In this lecture here, we want to start chapter 2 of our course, and this is going to be talking about functions and graph. In this first lecture here, section 2.1, we're going to be talking about the basics of functions, okay? So maybe in some of your other previous math courses, you may have heard of this function idea before. Okay, so this is really like a key concept for the rest of the course, okay? And then we're also going to talk about their graphs. So what are these graphs, okay, what they look like on the x and y axis. Okay, we're going to plot graphs of these functions. So, all right, so this lecture is going to be a long lecture. So there's going to be a lot of things we're going to talk about. All right, we're going to talk about find the domain and range of a relation. So actually the first thing we're going to do is define what a relation is in mathematics. Then we're going to determine whether this mathematical relation we have is what's called a function. Okay, so then we'll define what a function is. And then we'll determine whether an equation, if I just give you an equation, if it represents a special type of function. Then we'll talk about how you evaluate a function. Then we'll graph some functions by plotting points. This is kind of a review just with new notation. So I'm not going to spend too much time on this. So I'm going to burn through this, but I do have a lot of examples of plotting functions. Then we're going to introduce something called the vertical line test to identify functions. Then we're going to obtain information about a function from its graph. So this is going to be kind of like an application problem. Then we're going to define the domain and range of a function from its graph. And then what we're going to do is we're going to look at a function's graph and identify the intercepts. So there's a lot going on in this lecture. And I'm going to fill it with a lot of examples. And so we're going to, after I'm going to introduce the concept, we'll look at some examples of it. And hopefully that'll kind of like iron home the concepts. All right, so what is a relation? A relation is any set of ordered pairs. So ordered pairs are going to show this relation or relationship between two variables. And we usually see these ordered pairs listed as x, y. Okay, that's the most common thing. All right, so anytime you see an ordered pair, it's a relation. It explains how x and y are related to each other, okay? Now, if you have a set of ordered pairs, okay, like more than one, okay, the set of all the first components, x, in the ordered pairs is called the domain. So think of the domain here as the x values of the ordered pairs. You can also think about this as the inputs of the function. That'll make sense later on when I introduce functions. Okay, think of it, domain as the input. And the range, you can think of these as the y values of the ordered pairs. Okay, so going on here, the set of all the second components, is called the range of the relation. So the second component here is y. So the y values, the range is the y values of the ordered pairs. And think of this as the outputs. Okay. So if you think about like how we talked about graphing before, like you picked your x value, you picked it, you inputted it into your equation, and you got the y value, which was the output. Okay, so the domain is all the x values, and the range is all the y values. All right, so let's do an example here. So find the domain and range of this relation. So we have this set here, and it's just a set of ordered pairs. Okay, so remember, all of these values here, these are in the form x comma y. Okay, so the domain, all right, the domain is itself a set. Okay, so the domain of the relation is the set. So it's a set of all the x values. So look, 0, 10, 20, 30, and 40 is the domain here. So 0, 10, 20, 30, and 40. And now the range is all the y values, okay? All right, so it looks like 9.1, 6.7, 10.7, 13.2, and 21.2. Okay, these are the y values. Now, you generally do not have to put this in order with each other. Okay, so generally when you're gonna have this set, I'm gonna arrange this from lowest to highest, ascending order. Because what you're not going to do is you're not going to just rebuild the ordered pairs from looking at the domain and range like that. Okay, it doesn't necessarily always have to be in order. All right, so we kind of have this idea of what a relation is. All right, it's a set of ordered pairs. So what a function is? A function is a correspondence, okay, from the first set called the domain, we got that, to the second set called the range, which is the y. Okay, so remember the domain is the x values, and the range is the y values, such that each element in the domain, okay, each element in the domain corresponds to exactly one element in the range. Okay, so let me just kind of like visually show you what this means. So you have this domain and you have this range. Okay, and I'm just going to write the numbers like this. Maybe the domain is 5, 10, 15, 20, and the range is -1, -2, 0, and 7. I don't know. Okay. What this is saying is, look, you have a relation if, all right, a function, the relation is a function if each input domain corresponds to exactly one value in the range. Okay? So it can be like this. Now, let me show you another one that works. 1, 2, 3, 2, 4. This is also a function. All right? So even though these two x values go to the same y value, all right, each x value still only points, the 1 only points to one value, the 2 only points to one value. So both of these are a function. This would be something that's not a function. Something where you'd have 1 points to both 1 and 7, okay? And 3 points to both 9 and 10 here. So notice how the one value points to two different y values here. The one value, the x, goes to two different y values. This over here is not a function. Whereas this and this, both a function. Okay? So each x goes to only one y. Okay, that's how you can tell it's a function. All right, let's determine whether these here, okay, these here is a function. Okay? So look, 1 goes to 2, 3 goes to 4, 6 goes to 5, 8 goes to 5. Now remember, a different x value can go to the same y value, but long as the x's don't repeat, this is a function. So each x goes to one y. All right, that's what we want. 3 goes to 0, 4 goes to 0, 5 goes to 1, 6 goes to 1. Notice the x's don't repeat. So yes, this is a function. But now look at this one. This is saying -1 goes to 3. That's okay. 2 goes to 3. But it's also saying 2 is also, it has a relation with 5. But so this right here, when 2 goes to 3 and 2 goes to 5, this is not a function. As the x value 2 goes to both 3 and 5. So you have one element in the domain going to two elements in the range. That's not good. Not good. So whenever the x's repeat themselves, not good. You can't. You're not a function. All right. So if an equation is solved for y and there's more than one value of x can be obtained for a given x, then this equation does not define y as a function of x. Okay. So if you wanted to say, okay, is the relationship between x and y, okay, is it a functional relationship? Is it a function? If you could take that equation and solve it just for y, and you're going to notice that you're going to get, each x value is going to give you more than one y value, it's not a function. Okay, so that's going to be a little confusing, but let me show you here, okay? So determine whether the equation defines y as a function of x is the following. X squared plus y squared is equal to 1. Okay, so to check, let's solve for y. So the first thing I'm going to do is I'm going to subtract the x squared over. Now, you got to solve for y. So you're going to take a square root to solve, okay? But remember, when you take a square root to solve an equation, you get two solutions. So look at that. So notice for each x value you plug in, for certain values of x, okay, you're going to get two answers, a one positive and one negative. So thus, each x value here, okay, is going to give two y's. Okay, so in that case here, now what that means is if you plugged in the number, 0 for x, you're going to get plus and minus 1. So it's not a function. Okay, so whenever you get something like this, and you'll see later on in the class, this is actually a circle, and it's going to violate, later on in this lecture actually, it's going to violate something called the vertical line test. Okay. So next, if we know we have a function, okay, we use special notation to write it. Okay, so you see this notation here, f and then in parentheses x. This is important. This is not called f times x. This is called f of x. Okay, so f, it's a function of the x variable, right? Represents the value of a function at the number x. Okay, so what this is, another way of thinking about this. If your ordered pairs x comma y, okay, are a function, then we replace or call y as f of x. So as long as it's a function, f of x here is just another way of saying y. That's it. Literally, that's it, okay? Just another name for it. Like, for example, my first name is Matthew, but some people call me Matt. Okay, it's just another way of saying y in this case here. Okay, so let's talk about evaluating a function. So consider this. I'm going to do this example first. Let's consider just this. Y is equal to 2x plus 3. If I asked you to solve for y when x is equal to 2, what you would do is you would plug in 2 for x. Okay, so this plug in. So you'd go y is equal to 2 times 2 plus 3, which is 4 plus 3, which is 7. Okay. Now, if I just said, okay, consider this. F of x is equal to 2x plus 3. Okay. Let's evaluate f of x when x is equal to 2. So just like you did before, okay, you're going to say, okay, look, f of x is just another way of saying y in this case, okay? And I'm going to take this 2 and I'm going to plug it in for x. So you're going to go f of 2. So you're plugging in. And now this is saying, okay, I'm inputting. This is why I said x is your inputs. So whenever I see an x, I'm going to replace it with this input. It's 2 times 2 now plus 3 is equal to 4 plus 3 is equal to 7. All right, so you can see what's going on here. I'm taking the value and I'm plugging it into the function, okay? That's how you use this function notation. Just another way of saying y, okay? All right? But this is saying, okay, what are you inputting into my equation? I'm inputting the value 2, so I'm going to plug it in here. All right, let's do another one. All right, let's consider this. Let's consider the function f of x is equal to x squared plus 3. All right, let's evaluate 4. So I'm going to plug in, here's the first one. X is equal to 3. So what that means is I'm going to take 3 and plug it into the function. Now wherever I see the x, I'm going to replace it with 3. So this is 3 squared plus 3. This is 9 plus 3. This is equal to 12. Let's try this one. Let's plug in x is equal to negative 2. So I'm just going to take it and I'm going to plug it in. So this is negative 2 squared plus 3, which gets me 4 plus 3, which is 7. Now look, you don't always just have to plug numbers in. Okay, watch this. Let's plug in x is equal to a plus 1. All right. So this is, I'm plugging into the function an algebraic expression. It seems weird, right? So this is my input. Okay. So my equation is saying take your input and square it, and then add 3 to it. All right, well, what am I inputting? What am I inputting? I'm inputting not a number now, just I'm inputting a plus 1. And you could FOIL this out, right? Like this becomes a squared plus 2a plus 1 plus 3, which ends up being a squared plus 2a plus 4. All right, so you don't just have to plug numbers into these functions. You can plug in other algebraic values. Okay. All right, but you'll get a chance to practice this. Okay. But let's move on now. We just want to talk about graphs of a function. So the graph of a function is the graph of its ordered pairs. Okay. So just recall, ordered pairs are shown as x comma y. All right, but for a function, we're just renaming y is equal to f of x. So the ordered pairs are now shown as, so the ordered pairs are now shown not as x comma y, but x comma f of x. All right, so when you go to plot these, this f of x is still plotted on y-axis. It's still plotted on the y-axis, right? All right, let's try and let's do just a couple graphs. Okay, so I've got the axis here. So let's sketch the graph of, here'll be the first one. The function f of x is equal to, let's look at 2x, let's just do minus 1 here. All right, so the way you would graph this is you would set up a table of values. So here you'd have to pick your x's and you'd use them to get your y values. Okay? And then you'd want from that, what you'd have is you'd have your ordered pairs, your x comma, not y, but in this case, f of x. So remember, over here, this is, y is just another way of f of x. So I'm just gonna very simply do 3 values here. I'm gonna do negative 2, 0, and 2, because it's a straight line here. So f of negative 2 is 2 times negative 2 minus 1 gets me minus 5. So my first ordered pair is minus 2, minus 5. F of 0, I'm plugging it in, so 2 times 0 minus 1. Well, that's just minus 1. And then 2 times, so f of 2, I'm going to plug it in, so this is 2 times 2 minus 1. Well, that gets me 3. So 2, 3. And you can see here that this function, it's just a linear function, right? So not the best straight line, but you get the idea. All right, let me mix it up. Okay, let's try this one. And this is going to seem weird now, okay? Let's look at the function f of x is just equal to the number 3. That's so weird, okay? So I'm setting up my table of values here. So I'm going to pick some numbers again. I'm going to pick -2, 0, and 2. Well, what is this saying? Look, whenever I plug in -2, whatever I'm plugging in, it doesn't matter what it is, I get 3. Okay, so let's plot this point. -2, 3. f of 0. Well, when I plug 0 in, the function is saying you still get 3. So 0, 3. All right, let's try this last one. f of 2. Well, no matter what value I'm plugging in for 2, the answer is still 3. Do you see what this is here? Okay, this is just a horizontal line. Great. And let's try this one next. Do another one here. Let's look at f of x is equal to 2x. Let's look at f of x. Yeah, let's look at 2x squared minus 1. Sorry about that. Okay, so I know the squared. I see the squared term here. So I've seen this in some of the other lectures I've done. So this is going to be this is a polynomial function, and the squared term tells me it's going to be a parabola. Okay. So I'm going to do a bunch of points here. Okay, if you plug -2 in, right? -2 squared is 4 times 2 is 8 minus 1 is 7. F of -1 squared is 1 times 2 is 2 minus 1 is 1. F of 0. Well, 0 squared is 0, so this is just -1 is left. And then f of 1 here, 1 squared is 1, times 2 is 2, minus 1 is 1. And then again, f of 2 here is the same as f of -2, gets me 7. So let's plot it, see what we get. -2, 7. -1, 1. 0, -1. 1, 1, and 2, 7. So you get this, you can see the U-shaped here, right? All right, let's do a graph that next, something we've haven't actually done before. All right, so let's sketch the graph of this one here. Let's look at f of x is equal to just the square root of x. Okay. So remember, so first off, it's like, what does this graph look like? Well, I'm going to find the table of values. So can you take the square root of a negative number? No. So no negative values for x. So I'm going to start with 0. Okay? So f of 0 is the square root of 0, which is 0. So 1 point is 0, 0. I'm going to pick 1. Well, the square root of 1 is 1. So then my next point is 1, 1. Now what I'm going to do, well, I'm going to take the square root. So I'm going to pick a number that I can actually take the square root of, which is 4. So the square root of 4 is 2. So you didn't want to pick the value 2, okay, because what would happen is like, well, square root of 2, nothing easy. So what's the next perfect square? It's 9. So f of 9 is square root of 9, which is 3. So 9 is off the scale here, so it's probably over here, something like this. And you can see here, it's like this. That's actually, it looks like 1/2 of a parabola on its side here is what this graph is going to look like. And remember, no negative values of x. So it's just this graph right here. Like that. Okay. Let's move on and talk about if you're given a graph, how do you know if it's a function? So we have this thing called the vertical line test. So if any vertical line intersects a graph in more than one point, the graph does not define y as a function of x. Okay, it's not a function. So if you look here, all right, if you have these two graphs, right? So you have this one here, like this. If you draw a vertical line through this blue line, notice how it hits the graph twice. This is not a function. Whereas the parabola here, any vertical line you draw through only hits the graph once, so it is a function. Let me put some other ones up there just so you can see. So draw a vertical line through and see if it's a function. So imagine if you have a graph that looks like this. Well, look, if you draw a vertical line like this, fails the vertical line test. So it's not a function. Even if you have just something that looks like this. Okay? And it only does it just very, very briefly. Right? It's still right here and here. Fails the vertical line test, because any vertical line, doesn't matter if it only does it once, it still fails the vertical line test and is not a function. But if any function, whatever it looks like, as long as you can only draw a vertical line through it once, across the entire function graph of it, then it is a function. But even if it's just only in small parts, boop, 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 like right here, fails it, not a function. All right, let's do an application problem now. All right, so I've got this graph here, and what you see here is it's showing T cell counts and HIV infection here rates. Okay, so this right here, what this shows, this graph shows the average T cell counts. Okay, and it's unfortunately it's for people who are in different stages of infection. So you can see here in this color here, all right. This is asymptomatic stage where they're not showing any symptoms. But then once they start to show symptoms, you can see that their average T cell count starts to fall. And then finally, when they're have a AIDS clinic diagnosis, you can see that their T cells even following. So what's going on here is x, our x variable is time and number of years, and our y value, f of x here, it's the average T cell count. It's giving the average T cell count. All right, so it's saying, look, this is a function. Okay, it's a functional relationship because it passes the vertical line test. So it is. We want to use this graph to find f of 5. So this is the input. So this is when x is equal to 5. So you're going to go to x is equal to 5, and you're going to go up here. And you're going to see it's 400. Now let's try this one. Now it's asking you to find what value of x is the function equal to 200. Well, here's 200. It looks like that happens when x is equal to 8 right here. So when you look at the graph, you can find values of x and y by forming ordered pairs in either direction here. Like in this one here, we found the y value because we're given the input. Here we found the x value because we're given the output of 200. All right. So now what I want to do, we've got two more topics. We've got domain and range from a graph, and then we've got intercepts. So I know this is a longer lecture, but we're coming to the end. So now I want to talk about identifying the domain and range of a function from its graph. Okay, so use this graph. So we've got this graph here. It looks like just this blue line here, okay, to identify its domain and range. All right, well, look, so the domain is the x values, okay? And the range is the y values. All right, so look, notice how this graph, okay, it's defined, okay? The blue line goes from x is equal to -2 all the way up to 1, okay? So it's all the values in between. So it looks like the domain, and I'm going to show it in interval notation. Looks like it's going to go from -2, the x values here, to 1. All right, so you can show it in set builder notation. It's the x such that all right, now let's do the x such that x is between -2 and 1 there. So the range is interval. I'm going to do it as an interval, and then I'll do it in set builder. All right, so this is the y value. So look at the y values the graph takes on. It looks like the lowest possible y value is 0, because this is 0 along the y-axis, and then it goes up until 3. So it looks like it's 0 to 3. Oops, sorry, I did that a little backwards. 0 to 3 in interval. And then in set builder, it's now the y values such that y is between 0 and 3. All right, let's do another one here. Okay, so now notice, this is really important. Notice I have an open circle here, not a closed circle. Like in the previous example, these closed circles mean it goes and includes the endpoints, okay? So the domain. Well, look, it's the x values. So it's going to go to -2, but it's open circle or open bracket. And then the x value goes whoop all the way to 1. This is 1 along the x-axis, and this is closed bracket. So it's the x values such that strict inequality, -2 is less than x, which is less than or equal to 1. And the range, well, looks like, now this is important. It starts, what value is this on the y-axis? This is -1. Closed circle, so it's going to include -1. And it goes all the way up to 2, but open circle. So it's the y values such that -1 is less than or equal to y, which is strictly less than 2. All right, but now let's try this. Okay, I've got this graph that looks like this. Okay. Well, look, notice how this graph goes up. So this arrow means it goes up and out forever. And this arrow means it goes down and all the way to the left forever. So if it's going to keep going to the right and to the left forever, and there's no breaks in it anywhere, okay, the domain is going to be all real numbers. So it's going to go from -infinity to infinity. And the range, look, the range is saying this is going all the way up forever and then all the way down forever. There's no y values missing. So this one, the range is also all real numbers. And that's okay to have these. Generally when you have a polynomial function, which this is some type of cubic function, the domain and range will be all real numbers. All right, let's do the last thing here, talking about identifying intercepts from a function's graph. Okay, to find x-intercepts, just look at the point where the graph crosses the x-axis. To find the y-intercept, look for the point where the graph crosses the the y-axis, excuse me. And this is important. A function, this is just for a function. A function can have more than one x-intercept, but can have at most one y-intercept. Okay, so it can only have up to one y-intercept, but it can have multiple x-intercepts. So let's go back and look at this function here. All right, and look the x-intercepts. The x-intercept, it looks like it crossed the x-axis at -3, -1, and 2. Well, these are ordered pairs, the intercepts. Okay, the y value at the x-intercept is 0. So you're going to have to remember, whenever it asks for ordered pairs, remember, show them as points. So intercepts are ordered pairs. And look, the y-intercept is at -6 down here in the blue. So the x value is 0, all right, at the y-intercept. All right, class, I know this was a little bit of a longer lecture, but I hoped it helped with the understanding of functions, how to graph them and evaluate them. And, you'll get a chance, as always, to practice this.